Hello, and welcome to this update on the development of the Davenport Flood Resiliency Plan. The consulting team of H.R. Green, Sasaki, and Shive Hattery has been working since last August to assist the city in developing a plan that will improve resiliency, increase operational efficiency, and enhance transportation routes during Mississippi River flood events. As we've described in previous presentations, this study has several components. It includes engaging with the public and stakeholder groups, like we're doing here today, considering land use changes and mitigation alternatives to increase resiliency to flooding, reviewing the city's flood operations plan to identify areas for improvement, considering transportation, safety, and mobility across the city during flood events, and finally, putting together a funding and implementation strategy that will become the heart of the plan moving forward. As I mentioned, we began our work in August of 2020 with a robust data collection and analysis effort. This included reviewing data provided by the city, as well as gathering input from the public and a variety of stakeholder groups. Over the winter, we've taken that information and worked with the city to develop draft goals and concept alternatives for the flood resiliency plan. We are now reaching out to gather feedback on that work so that we can refine the vision and develop recommendations for the plan. The purpose of the presentation today is to describe and gather feedback on three main questions. First, what is being considered, including the priorities and guiding principles, the flood risks, and the type of solutions. Next, we'll go into the impact of flooding at a range of flood stages and consider the criteria to use when evaluating alternatives. And finally, we'll present examples of potential solutions that would address two different levels of flooding. The first being an array of options that would increase resiliency and reduce operational effort for major floods that fall in the range from about 18 feet of stage to up to 22 feet flood stage. The second set of potential solutions will consider a target elevation of flood stage 24 and what a continuous system of flood mitigation at that level may look like. So let's begin. Last fall, we reached out to a variety of stakeholder groups and the public in general through an online survey to ask a series of questions related to flooding, the city's flood response, and people's relationship to the river and the place where they live and work. These are some of the themes that came out of that effort. When we asked people what the city's priorities should be in responding to high river levels, we heard access, specifically related to flooding impacts on transportation routes, the impact of flooding on businesses, community facilities, and infrastructure, and the impacts on people and residences. People noted many things that make Davenport special, including local businesses, outdoor spaces, relationships with the community, and the ability to get out and about. When we specifically asked about how the riverfront could be improved to increase the number of visitors, we heard there needs to be more things to do, improvements to access, more natural areas to enjoy, some level of flood protection, and better maintenance and cleanliness of the riverfront. After gathering data from a variety of sources and considering the input from the public, we worked with the city to develop a set of guiding principles to reference when developing flood resilience concepts. The four goals are listed here. Starting with resilience, we want to reduce the impact of flooding on day-to-day lives and economies, including the ability to recover more quickly from a flood event. We also want to reduce the operational drain that flood fighting has on the city's resources. In making improvements, there is a desire to do so in a way that provides a balanced investment in flood mitigation and flood fighting across the full riverfront. And finally, public access to the riverfront as a public amenity needs to be prioritized. For the purposes of today's presentation, we're going to discuss flood mitigation efforts at three different levels based on flood stage. In the first level, we have major floods that range from approximately stage 18 to 23 feet. This includes all the major floods that Davenport has experienced to date, including the flood of record in 2019, which reached stage 22.7. The second level is stage 24, which is approximately the 1% chance or 100-year flood event, and a little more than a foot above the flood of record. And finally, the third level we have is stage 27 and up. Infrastructure to this level would be required if the goal were to build flood mitigation in the form of levees or flood walls that would have the necessary freeboard to be accredited by FEMA and remove areas from the regulatory floodplain. In today's presentation, we're only going to focus on a variety of structural flood mitigation strategies aimed at reducing or avoiding the impacts of flooding. Non-structural mitigation strategies, such as changes to regulations or zoning, flood warning and response plans, buyouts, or flood-proofing of individual buildings, are not covered in today's presentation. And finally, what we're going to present today when describing the concept alternatives are only examples of the many possible combinations of strategies that can be used to address flooding at any of the flood levels. Certain strategies are more relevant, feasible, or effective at different flood levels, but each has their place in a comprehensive flood plan. So let's talk about flood risk and the impacts of flooding at the different levels. Recall the three levels of flooding being considered for today's presentation. Flooding in the major floods category has occurred a number of times in the period of record, which dates back to 1878. In that time, the Mississippi River has reached flood stage 18 on 273 days and flood stage 22 on 18 days. In the more recent past, looking back just over the past 20 years, the river has reached stage 18 on 142 days and stage 22 on 7 days. As I mentioned earlier, the 2019 flood of record was stage 22.7. As a point of reference, stage 22 is approximately equivalent to the top of the seawall upstream of the dam, up near the East Village. Flooding to stage 24 approximates the 100-year flood event, which has never been reached during the period of record. However, there is a 1% chance of the river reaching this stage in any given year. And finally, stage 27 would be the approximate target elevation for a FEMA-accredited flood mitigation system. Looking back over the history of flooding in Davenport, as measured at the Rock Island gauge, we can see that a number of large flood events have occurred over the entire period of record. But you can also see that larger flood events are occurring more frequently in recent years. So what does flooding look like in Davenport? Referring to the city's flood inundation maps, we can see that at stage 18, there start to be significant impacts to the riverfront parks and River Drive, and that flooding occurs in low-lying locations, even away from the river, due to water backing up through the storm sewer system and surcharging onto the roadway. A significant effort in flood fighting is made by the city at or below flood stage 18 as well. In fact, over half of the city's flood response actions occur at or below stage 18, representing a significant investment of manpower and materials. By stage 22, the flooding extends well inland of the seawall, significantly impacting transportation routes, access to the government and Centennial bridges, as well as homes and businesses. At stage 24, water would be over the seawall even upstream of the dam, reach the main concourse of the river's edge center, and impact the water pollution control plant, and as you can see, inundate several city blocks north of the riverfront. And by stage 27, the river would flood even further inland and reach the bottom of the government bridge deck. As we consider the impact of flooding at various stages and the potential strategies that we might employ to meet the goals of improved resilience, reduced operational drain, equity, and public access, we need to put in place a series of criteria to measure and evaluate the options. The evaluation criteria we have developed for each goal are listed here. For resilience, we want to look at flood stage impact as measured in feet. For example, if a strategy changes the flood impact for a specific location from being flooded at stage 15 currently to not being flooded until stage 18, then we would have gained 3 feet of stage by employing that strategy. For operations, we want to consider the current flood fighting effort required versus the future flood fighting effort required, and also the effort it will take for the city to implement a particular strategy in terms of the difficulty and timeline for completing a project, as well as the capital cost of construction. In terms of equity, we can measure the number of days an area has been flooded in the past and also consider the people affected by looking at metrics such as the number of occupants. Finally, when considering public access, we take a more subjective view of how each potential strategy may have opportunities for co-benefits that preserve or enhance the public's connection to the riverfront. Before we get into the discussion of potential mitigation strategies, I want to pause here. We want your feedback on the city's priorities and goals for improved flood resilience. Please share with us your priorities when it comes to developing the flood strategy. The next part of the presentation will describe a number of concept alternatives for structural flood mitigation. The types of strategies we are presenting here fall into 4 main categories: underground infrastructure, raised roads, flood wall, and landscape berm or levee. Underground improvements generally involve adding gates on storm sewer outfalls to prevent river water from backing up through the storm sewer system and inundating low-lying inland areas. This often requires some reconfiguration of the storm sewer system, the addition of the gate, and potentially permanent pumping to discharge stormwater collected in the interior area during rainfall events. Raised roads are just like they sound. They involve building up the road elevation above the flood level. Landscape berms and levees can be used when a higher level of flood protection is desired and where there is adequate space. These can often be incorporated into public parks or green spaces. Finally, flood walls are often employed when that higher level of protection is needed and space is at a premium. As I mentioned before, it is unlikely that any one strategy would be used exclusively, and very likely that a combination of strategies are deployed. At the lower stages, underground improvements and road raises tend to play a larger part, whereas flood walls and berms become more important tools at stage 24. Once mitigation measures become even taller, like at stage 27, flood walls tend to dominate the alternatives due to the lack of space that would be required for the other types of infrastructure. Structural mitigation improvements could be made with either of 2 quite different visions in mind for the future of flood response in Davenport. The first vision may look to continue Davenport's history of flood response, but to make permanent incremental improvements that would increase resiliency, improve access, and reduce flood fighting effort and costs, while not creating any sort of continuous riverfront flood protection system. This strategy would tend to focus more heavily on storm sewer and roadway improvements and would have relatively lower capital costs. The second strategy might envision setting a target flood elevation for the entire riverfront, likely above the flood of record, and build a continuous flood mitigation system that would come at a much higher upfront cost, but would greatly reduce flood fighting efforts and provide widespread flood protection through underground utility improvements, seepage mitigation, and above-ground flood walls and berms. The options really run along a continuum from more incremental infrastructure improvements all the way to significantly transforming large portions of the riverfront for permanent flood mitigation purposes. We will present infrastructure options in the subsequent slides with these 2 differing visions in mind, starting with the more incremental improvements approach, followed by a discussion of improvements to achieve mitigation to flood stage 24. Please remember, the concept alternatives described are only examples of the possible combinations of strategies that can be used to address flooding at any of the flood levels. We'll start with examples of incremental improvements. And we'll discuss these in 4 different sub-areas of the riverfront, starting with Area 1 on the east end and moving downstream to Area 4 on the west end. Starting in Area 1 in the village of East Davenport. This area currently experiences road flooding on River Drive and Mount Street as river water surcharges out of the intakes at stage 19.5. One strategy to keep the road open would be to separate the upland storm sewer from the floodplain storm sewer and install backflow prevention on the floodplain storm sewer system. Temporary or permanent pumping would be needed during rainfall events. This option would keep the roadway open for an additional 2.5 feet of stage until flooding came over the seawall. The project has a relatively low construction cost, but would continue to require some level of operations effort to close gates and set pumps. Another option to keep River Drive and Mound Street open to higher flood stages would be to raise the low portion of the roadway. Raising the roadway approximately 3 feet would keep River Drive open to stage 22. Let's move downstream now to Area 2, which covers the riverfront from approximately 4th to Gaines. Looking at this area in the lower right corner of this map, flooding of River Drive begins to occur at stage 17.4 when river water comes out of the storm intakes. Separation and backflow prevention could be used to keep the road open longer. Alternatively, River Drive could be raised from the intersection of 4th and River to east of Tremont Avenue. A road raise of approximately 3 feet could keep this section of River Drive open to stage 22. In addition to keeping River Drive east of 4th open, targeted road raises at LeClaire and 3rd and at Gaines and 2nd could provide permanent access to the Government and Centennial bridges from 4th Street up to stage 22. Looking at incremental improvements further downstream now in the area from Gaines to Division. In this area, there are several opportunities for storm sewer improvements. For example, river water that has backed up through the storm sewer system begins to flood the roadway on Myrtle at stage 14.5 and at River Drive and Marquette at stage 15. By separating storm sewer systems and installing backflow prevention, this section of River Drive could remain open until overland flooding occurs at around stage 18, a gain of 3.5 feet of stage. Changes to the configuration of the storm sewer system could also simplify the flood response and pump operations. Other incremental improvements that could be made in this area include road raises on 2nd Street and Rockingham Road to create a longer continuous section of roadway that sits above flood stage 22 for better access during flood events. Moving on to Area 4, west of Division into West Davenport and the Credit Island area. One incremental improvement that could be made in this area would be improving the access to Credit Island by reconstructing the causeway with more flood-resilient materials so it could stay in better shape and be accessible sooner after a flood event. Better flow into the slough and ecological uplift could also be realized through the addition of more culvert area or a bridge opening. So what is gained by making these types of incremental infrastructure improvements? Using the examples provided here and referencing previous studies, for an overall investment in the range of $12 to $18 million, there could be improved access to the Government and Centennial bridges. The city could delay the start of flood fighting in certain areas until higher river stages, which would reduce both disruption to the public and labor costs. The city could establish a permanent detour route across Davenport that would be open to stage 22, capitalizing on some strategic sections of road raises. And finally, the city could fix and rehabilitate its existing stormwater pump stations. Of course, the options discussed here are not the only options that could be employed in this incremental fashion. There are areas where landscape berms or flood walls could provide similar types of benefits at strategic locations that would reduce the overall flood response effort through eliminating or simplifying flood fighting actions or increasing the flood stage at which flood actions need to commence. Switching gears now, we want to provide examples of strategies that might be used if the goal were to provide a continuous system of flood mitigation along the riverfront, in this case to stage 24. Again, we'll be looking at the areas along the riverfront from east to west. Starting in the village of East Ave. Before we dive into the various strategies, one concept that we want to make clear is that when constructing any type of continuous flood mitigation system, there are required underground improvements that must be made. These include reconfiguration and backflow prevention for the storm sewer system, addressing all the other underground utilities that cross the line of protection, installing seepage mitigation, and addressing interior drainage during coincident rainfall events. That can be done through either temporary or permanent pump stations. For clarity, these improvements are not shown on the subsequent maps, but they are an integral part of building any above-ground improvements that will be discussed, and they are often just as expensive to implement. As you can see on this map, the area of impact is much larger at flood stage 24. Looking at a section cut near Mound Street, the flooding at stage 24 would look something like this. One option for this area would be to build a flood wall north of River Drive that would stretch east and west of Mound Street to tie into high ground and would include a removable road closure. A variation on this alignment north of River Drive would be to replace sections of flood wall with landforms in the areas with adequate open space. In section view, the flood wall option might look like this. And the landform option in Lindsay Park like this. A third option for this area could be a flood wall along the south side of River Drive, between the roadway and the railroad, with a removable closure across Mound Street. The length of this wall would need to be longer than the alignment on the north side, and therefore has a higher cost. In section view, this option would look something like this. While this alignment would keep River Drive dry to stage 24 near the East Village, one item to note is that River Drive is inundated in Bettendorf below stage 24. One more option for this area would be to raise River Drive itself for the extent that it floods up to stage 24. This would require some reconstruction of Mound Street as well to tie in. In section view, the raised road option would look something like this. Again, East River Drive and Bettendorf would still flood below this stage. Moving west now to look at options in Area 2. Again, I remind you of the baseline underground utility and seepage mitigation improvements that must be completed with any of the above ground options. You can see on this map the large area of impact at flood stage 24, extending a couple blocks inland from the river, which looks something like this in a section view. The first option for a continuous line of flood mitigation in Area 2 seeks to provide access to the city's facilities located along River Drive up to stage 24. Starting at the east end, a flood wall option could include an alignment along the riverfront trail that would tie into high ground near Bridge Avenue and at the Government Bridge abutment, and then would continue west of the bridge along the north side of the tracks through the riverfront parks until it tied in with the flood wall at the ballpark and then continued on into Area 3 to the west. Some complicating factors that add to the cost of construction in this area are many underground utilities in the corridor and the need for flood closures across several roadways. Keeping alignment on the north side of the tracks, however, would allow for interim tieback locations to the north without having to cross the railroad tracks if the overall alignment were completed in several projects phased in over time. This section shows what this option might look like near the Sky Bridge. Grading elements of Main Street Landing may be worked into the flood mitigation, as shown here. Elevated park space between River Drive and the flood wall masks some of its 5 to 6 feet of height from downtown. Using a vertical barrier allows for more usable space behind the wall. A variation on option A, option B incorporates more landforms into the line of protection and less flood wall. The option of using berms instead of flood wall near the Sky Bridge is shown in this section. Grading of a berm reduces some of the usable space in the park compared with a flood wall. This option moves the alignment south of the tracks through the parks in the form of a landscape berm. Which is seen here in section view as elevated park space on the river side of the railroad tracks. The numerous at-grade rail crossings will play a big part in determining the grading options north and south of its tracks for any of these options. Moving west into Area 3, from Gaines to Division, you'll see similar options as were presented in Area 2. Again, we remind you of the baseline underground utility and seepage mitigation improvements that must be completed. Area 3 tends to sit lower in elevation than Areas 1 and 2, as you can see in the extent of the flooding at Stage 24. Option A for this area has more of a flood wall focus, extending the wall from Area 2 past River's Edge in Centennial Park, then south along Marquette Street around the Public Works facility, and west until it ties into high ground in Veterans Memorial Park. While no above-ground improvements would be required in the area of high ground, seepage mitigation would be needed across its length. Flood wall would then continue west until it tied into an elevated river drive. Option B is a variation on option A that includes more landforms in the park and less wall. Moving on to Area 4, west of Division and into West Davenport and the Credit Island area. In Area 4, we once again have the same baseline underground utility and seepage mitigation improvements that must be completed. This area is more open with more ditches and channels and includes different types of storm infrastructure like culverts under the railroad. It also includes existing flood mitigation infrastructure along Blackhawk and Walnut Creeks. Flooding in Area 4 looks like this in section, occurring in the natural floodplain areas south of River Drive, across River Drive, and impacting private property on the north side of River Drive. One option for flood mitigation through this section would be to raise River Drive from west of the underpass to Blackhawk Creek, then extend a line of protection along the north side of Blackhawk Creek to tie into the existing Blackhawk Creek berm. This alignment would require a railroad closure. River Drive would also be raised past the railroad overpass to approximately South Fairmount Street. The road raise might look something like this in section view, potentially utilizing vertical walls where there are larger changes in grade, in order to reduce the width and impacts to adjoining natural areas. As mentioned earlier, flood mitigation berms exist along Blackhawk and Walnut Creeks in the Garden Addition area. To be part of the complete system to stage 24, improvements to this area would include the berm tie-in noted previously, closing a gap in the berm and adding temporary road closure at the South Concord Bridge, and making the necessary maintenance and seepage mitigation improvements to the existing berms. In addition, numerous interior drainage improvements could be made. Through a reconfiguration of the storm sewer, 4 outfalls to the creek could be eliminated and all storm water directed to a detention area and a single pump station with a gated outfall near location A. Rehabilitation improvements to the pump station itself mentioned under the incremental improvement section could also be made. So when you put it all together, a continuous, comprehensive line of flood protection could look something like this, with a cost range of $220 to $370 million to cover the entire riverfront end-to-end to stage 24. This would have no effect on flood maps or flood insurance. To reach that level of mitigation, an additional 3 to 4 feet of height on flood walls and berms would be required at additional cost. Continuous options like this could also be built to lower flood stages at somewhat reduced costs. The continuous system would include flood walls, landforms, interior drainage improvements, and pump stations, and really be a comprehensive system. Today we've presented some background information and a number of concept alternatives for structural flood mitigation. Now we want to hear from you before we move further along in the process. Our next steps will include gathering feedback from the online survey and stakeholder meetings, refining a preferred direction for land use planning, developing the recommendations for flood mitigation and flood response operations, and putting together a funding and implementation strategy, and finally bringing it all together into a flood resiliency plan.